All right, we're ready for the afternoon session. We got 3 talks. As you can see, we're sort of heading into this time of thinking about model discovery and what you can do with data towards dynamics and recovering engineered systems or governing equations in one sense. So that's kind of going to be a lot of the focus for the afternoon. Our first speaker, Steve Brunton from Mechanical Engineering, a great friend of mine. I'm super excited to, I've seen him talk a lot, but I always like to see Steve talk because it means I'm not talking. So he's going to be talking about discovering interpretable equations. And so Steve, take it away.
All right, thank you, Nathan. Thank you all for coming here. It's super exciting to have so many of you from Seattle and also those of you who are visiting us here. Really a pleasure for us to be here also. And I'm really excited to tell you about some of the work that we're doing in discovering dynamical systems from data, interpretable, generalizable, and useful dynamical systems models of physical systems using modern techniques in data science and machine learning. Before I start, I want to acknowledge a number of great co-authors and colleagues on this. Almost everything I'm going to talk about is work with Nathan Kutz in the data-driven discovery, and also with Jean-Christophe Loiseau, in particular with respect to learning fluid mechanics equations. And then I'm going to highlight a lot of great work from postdocs and grad students. And I know I'm missing some people. This is a huge effort, and really I'm just going to focus in on a couple of vignettes here. I love the word vignette that Michael also uses. I also want to acknowledge generous funding support from many agencies who have taken risks on this work early on before it was clear that it was going to work at all. So thank you all. So I'd like to start with this movie of an eagle because I think this gives us a lot of inspiration when we think about engineering systems and machine learning systems. So this eagle is really performing a pretty remarkable feat of, maybe you won't call it engineering, of natural performance. It's interacting with a very complex, multi-scale, high-dimensional turbulent gust field. And in this case, it is performing this maneuver to gently land on a rock. Now, there's a couple of features I like to think about when I watch this movie of the eagle. I've watched this movie hundreds of times. This eagle is interacting with a complex flow field, a system that I would argue is beyond our ability to simulate currently. We might be able to chop up a box of fluid and model the turbulence with a supercomputer if we discretized it with billions of degrees of freedom. But that would be neglecting all of the complexity of the compliant wing surface and the feathers, let alone the muscles and the neuromechanical control system that is all kind of rolled up into this very multi-scale complex system. Yet the eagle is able to effortlessly and seamlessly interact with this complex system and perform incredible, robust control feats that are far beyond our ability on similar scale platforms. So this is inspiration for us. We're going to keep showing this movie until we get even halfway there with engineering systems. So you'll be seeing this for the next 20, 30 years at least. And I use it as a motivation for some of the principles that we use when building models from data. So what are some of those principles? Why can this eagle interact with this flow field when we can't even simulate it? Well, a couple of other features. The eagle probably doesn't know about Navier-Stokes equations. It does not have a PhD in fluid mechanics. And it does not have, importantly, full three-dimensional weight measurements that we would have from wind tunnel measurements or simulations. What it has is experience, and it has distributed sensors on its wing. Those feathers are actually feeling. You can almost feel it yourself when you watch it because we can picture ourselves in that situation. It has a great inertial guidance and control system. And so somehow it's coupling those various modalities of experience of itself in its life and its ancestors, these sensors, to feel the relevant features in the flow that it cares about for its daily life. So I would argue that the eagle doesn't care about all of those billions of degrees of freedom in the fluid flow. There are dominant, powerful, coherent structures in the flow, for example, leading edge vorticity, that it uses to maintain lift and drag and balance forces and moments in this case so that it can gently land on a rock. So it doesn't care about millions of degrees of freedom, and we shouldn't either. Okay? And the fact that there exist those dominant coherent structures facilitate its relatively sparse measurements. It doesn't need to measure the whole flow field or compute the whole flow field. Okay, so that's kind of this biological principle that from this massive data that you could be collecting and simulating and trying to understand, there are dominant patterns, dominant dynamics that actually matter for our daily lives that we might want to use for control. And we should be focusing our energy on sensing, modeling, and controlling those. Okay. So a couple of principles I'm going to talk about in this talk, and these are guiding principles that we think about in our daily research. Most of the time, when we learn about dynamical systems modeling and physics in a textbook and control theory, you start with equations of motion. You start with a double pendulum or a car, and you write down the Hamiltonian, you derive the equations of motion, and you start going from there. You linearize and you build controllers. But for most of the modern systems that we actually care about, systems of interest, we actually don't have equations of motion, or we can't agree on them. So think about climate or neuroscience or epidemiology. We don't have or can't agree on a governing equation for those systems. Even in turbulence, where we have an exquisite model in the Navier-Stokes equations, it's too cumbersome. It's an all-purpose general equation that works in all fluids. And presumably, it is not what we want to efficiently solve for the dominant coherent structures in this fluid. So even if we know the equations, we might want reduced order models that are useful for our engineering optimization and control loops. Okay, so that's going to be a key principle, is discovering models from data in a way that balances accuracy and efficiency, complexity and descriptive capability. Another key feature in general, and I think I've heard Nathan say that this is what keeps us all in business, I really like that, is nonlinearity. If the world was linear, we'd all be home right now, okay? Nonlinear dynamics are still extremely poorly understood. Even epsilon nonlinearity really hinders our ability to have general all-purpose solution techniques and computational architectures. And so what I'm going to talk about also a little bit is this idea that we can better learn dynamics from data if we know a coordinate system to measure in. And this is kind of a coordinated joint optimization problem. You want to learn models that you don't know, unknown dynamics, and you have to be listening to the right variables. You have to be measuring in the right coordinate system to do that. And if you think about the major advances that have happened in mathematical physics and engineering mathematics over the last hundreds of years, a majority of them, I would argue, can be lumped into kind of these large categories. Fourier discovered a coordinate transformation that made the heat equations simple. Okay? Maybe that's an oversimplification, but these are two massively important aspects in classical mathematical physics and modern mathematical physics, discovering equations from data in the right coordinate system. And so what I'm going to talk about is our approach, which is to learn these physical models from data, and we put a big premium on models that are both interpretable and generalizable. So we will use neural networks when useful and when needed, but we don't just want to have kind of a black box input-output system. We want to be able to get under the hood and see how the gears move and understand how our model works in a way that we can communicate and analyze and understand. In addition, I think very importantly, when we apply machine learning to physical systems, we shouldn't be throwing out hundreds of years of hard-earned knowledge. We know that energy is conserved and mass is conserved and momentum is conserved in systems. We know how, and we shouldn't be throwing that out. Okay, so if we can bake in the partial knowledge that we have, we're going to have a lot better time applying these to physical systems. We can also learn new physics, analogs of conservation that are maybe too complicated for us to have written down before. Okay? And again, I mentioned the existence of big patterns facilitate few measurements and low-dimensional computations. So we hope that our system actually does have some simple underlying description that we can uncover. And I really just want to emphasize, if I was going to pigeonhole, and I do like to pigeonhole, machine learning is optimization based on data. You are building models from data with optimization techniques. This is not magic. This is something that we've been doing for a long time. This is built on linear algebra, statistics, optimization. These are hundreds-year-old fields with lots and lots and lots of deep knowledge. And now we just have bigger computers and better modeling architectures and more data. And so I really think, this is about optimization. All right. Good, so I'm going to jump into model discovery, and I'm going to talk about how we view one path of discovering interpretable and generalizable models from data. This is not the only path. It doesn't always work, but when it works, it has some nice features. And I'll point out that this is, there are hundreds of papers I could put up here, and this has been going on for dozens of years, and really, really interesting work and progression of what I'm showing here. I'm going to zoom into kind of this decade of work where sparsity became a key role or kind of a key idea in models. And some people call it sparsity, some people call it parsimony. It's this idea that you're trying to balance accuracy and complexity of your model. All modeling in some sense, again, maybe I'm just gonna go on a bunch of overgeneralizations. All modeling is about finding the right balance between accuracy and efficiency. I could see like the full Navier-Stokes equation, very accurate, pretty slow. I could solve a very, very simple linear model, not that accurate, super fast. Okay, and you want to find that sweet spot, this kind of parsimonious sweet spot where you get the best of both worlds. Okay, that's what I'm going to talk about today. So there's this sparse identification of nonlinear dynamics algorithm that Nathan, Josh, and I cooked up a few years ago, with this simple observation that most of the dynamical systems that we play around with in textbooks, the mathematical engineering physics systems that we use as analogs to the real world, end up looking shockingly simple when you write them down. This equation, the Lorentz equation in 3 variables, has very, very simple right-hand side nonlinearities in the space of what could possibly be on the right-hand side. It's linear and quadratic. And there's only a couple of quadratic terms that pop up in this equation. Okay, so somehow we were on a big sparsity kick with compressed sensing and high-dimensional sparse geometry, and we started thinking this is really sparse in the space of polynomial functions on the right-hand side. And so it turns out you can do a lot with that idea, and I'll walk you through kind of how the Cindy algorithm works on the Lorentz equation, and then we'll build up to more complicated test systems after this. Okay? So let's say I measure the full state of my system, x, y, and z in time. So these are time series measurements. Each row is a measurement of my system in time. And let's say I also have derivatives x dot, y dot, and z dot. Now you know that's too much information for me to be assuming. We don't always get all of x, y, and z, and we almost never get all of the derivatives. But it's easier for me to explain when we assume we have all the information. We can break all of those assumptions later. Okay? And so one thing you could do, a lot of what we do in modeling is try to make it linear. I could try to build a little linear model with the dynamic mode decomposition. How many of you have heard of DMD? I think good, almost all of you. And if you did that, you would get a little 3x3 linear model here that would be the best fit linear operator advancing the state into the derivatives. And we know that that's not going to cut it for something that has this kind of chaotic nonlinear dynamics. Okay? So instead, what we can do is build up an augmented right-hand side library of candidate nonlinear terms that could be in the right-hand side equations. And each of these gray columns can be evaluated with the data I have in red, blue, and green. Okay, I have these measurements, and I can build all of these nonlinear columns. And now the task is to find the fewest columns in the right-hand side that add up to equal the x dot equation, the y dot equation, and the z dot equation. I'm saying the fewest terms because I fundamentally believe that if I measure my system in the right coordinates, it should be simple. The dynamics should be simple. There should only be a few terms that are active. Okay? And in fact, you can see which terms are active represented here in this C matrix, which tells you which terms are kind of there in the right-hand side, in the real equations. Now, if I did a least squares regression, which is what we've been doing for a long time, if I did a least squares regression, I would get a C matrix where all the terms are a little bit active. And we know that's an overfit model. I don't believe that this dynamics is explained with a model with 81 terms. That seems crazy. So instead, what we're going to try to do is find a C matrix which has as few non-zero entries as possible, corresponding to the essential physics that is required to explain the data. Now, in the olden days, this would be an NP-hard problem to find when I say find the fewest terms that add up in a library to the left-hand side, that used to be an NP-hard problem. You'd have to try all combinatorial possibilities of columns. But now with advances in sparse regression, so think of the lasso or what Sasha was talking about earlier, you can choose from any number of sparsity promoting optimizations. Now we can actually find the fewest terms in the right-hand side that add up to equal x dot, that equal y dot, and equal z dot. And when you do that, you uncover, just from the measurement data, the structure of which terms in the right-hand side were active. Okay, it's pretty cool. It works surprisingly well. And you end up uncovering both the structure and the parameters of the nonlinear dynamical system. So when I was growing up in dynamical systems, this was something we really, really always wanted to do and didn't know how. And with emerging techniques, in this case, in sparse optimization and building libraries, it now is relatively simple. Kind of a couple lines of MATLAB or Python. Okay, so I told you that we can break all of these assumptions, and I just want to tell you how some of these assumptions can be broken. So measuring the state and its derivatives is usually not how the world works. You usually measure a noisy state, and you have to compute your derivatives. So we wanted to make sure that we could do this from this kind of fuzzy, hairy Lorentz system here, where we're just measuring noisy x, y, and z. If you feed this data through this total variation regularized derivative, then you can get these kind of approximations to the derivatives here. And when you feed those into the SIMD architecture, you get the right structure of the dynamics. And almost all of the terms are quite accurate, except for this term here. It's off by 20%. But the rough dynamics, kind of the attractor and the behavior, are all there. You get the right structure and mostly the right parameters. Okay. So there's a lot I'm glossing over here, and our thought process on how the SIMD algorithm works has really evolved over the last few years considerably. So what I want to do is just walk you through some of the complexity. We used to think that the sparse optimization was kind of the neat part, because that's what solved the problem for us that we wanted to solve. Turns out the sparse optimization is in some sense maybe the easy part. We have experts like Sasha to cook up incredible algorithms, and they work. So what's the hard part of this optimization? So this is the thing we're basically trying to solve. I want to find some terms in C that explain my derivatives x dot, and I want to find the fewest terms of C possible. Okay? The things I glossed over there that are really, 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 really important are, did I measure the right variables in the first place? How did I know in Lorentz to measure x, y, and z? Like in neuroscience, you're not going to know what the right measurements are. That might be the hardest problem, is measuring the right coordinates. I gave you the data in the right coordinates here. We're going to have to learn the right coordinates. And that's what Kathleen's going to talk about in the next talk, is simultaneously learning the coordinates and the dynamics. I'm going to assume that she gave me the right coordinates. Okay? Now, if the other thing that's really important is I have this lambda knob, which tells me how sparse do I want my solutions to be. Remember, this is a trade-off between accuracy and efficiency. Do I want a really, really, really sparse model or a not so sparse model, and how do you choose that? Okay? And so the way this ends up looking, again, you have this kind of error complexity plot, and what you really want to be is down in this lower left corner. You want almost no error and the simplest model possible. And this lambda knob, I can sweep through this lambda knob and get sparser or less sparse models. And I'm going to walk you through what this looks like. Okay, this is not right. Okay. Okay, so if I have lambda equals infinity, so 1 over lambda is 0, then I'm basically going to get no terms. I'm going to penalize terms so much that I get the x dot equals 0 model, which is, as you might expect, very efficient to simulate, very inaccurate. Okay? If I have the lambda equals 0 solution, I'll recover least squares, which will be relatively low error, at least on my training data, but very, very complex. And you hope that there's some line connecting these two and some family of models between them. You actually hope it looks like this, kind of this Pareto curve that we've all heard about. And we want to find the models that live down here in the low error, low complexity limit. Okay? And I should really point out that in reality, the least squares solution is much, much worse when you apply it to cross-validated test data, because we don't believe that all of the terms are actually important for the dynamics. Okay? And so in these cross-validated sparse modeling, we try to find models here kind of in the sweet spot by sweeping through lambda, and we can either use cross-validation as a metric or information theory, and those generally work quite well. I'll point out that recently we have some work with Sasha. He talked about this. Sorry, this poker is dying. With Sasha and Peng and others, putting this into a unified optimization framework. So I highly encourage you to check this out for your applications, because this will work in a lot of applications much better. Okay, so there are kind of three challenges I talked about. There is choosing this lambda parameter to get parsimonious models to hit the sweet spot. There is measuring your system in the right coordinates, which is a fundamental challenge. It has been for hundreds of years. And then the last one is, how do I choose this library so that the dynamics are sparsely or parsimoniously represented in the first place? All of those are challenging. The sparse optimization is kind of the easy part now. We have efficient algorithms to do this. It's really about finding the right descriptive library, measuring your system in the right coordinates, and then choosing that sweet spot where you're balancing accuracy and efficiency. Okay? Now, fortunately for us, many systems tend to actually have polynomial nonlinearities. Even if you had nonlinearities that were non-polynomial, you might take an expansion and kind of use this, this asymptotic approach and model it that way. Okay, and a philosophical point I want to make. This is something that we've been thinking about very recently, maybe in the last 6 months, is I could try to put all of the burden on learning the best coordinate system so that my dynamics are linear. So that this model is actually linear. I don't need any nonlinearity. That's what Koopman and DMD try to do. Or I could take the measurements that I have and not do anything to them and try to learn a Cindy model that has as few terms as possible, but maybe I actually need a lot of terms because I was measuring a bad coordinate system. I think there's a sweet spot in the middle related to normal form. So we've been talking about kind of our classic education in normal form theory. There is a transformation where your coordinates aren't that bad, and you only have a couple of key nonlinearities, maybe cubic, maybe quartic, maybe quintic. Okay? And that's kind of what we're going for, and I think that's in spirit what Kathleen's going to talk about next. So in the last few minutes, I'm going to talk about how we've applied this to model fluid systems. Cindy would have just been a cute algorithm that we could pat ourselves on the back if it only works with the Lorentz system. But we got excited when we applied this to fluid systems and started to recover kind of the canonical reduced order models that took very smart people a long time to figure out. And so that's what I'll talk about here. I'm going to gloss over all of the history, but there's this rich 30-year history from Ruel and Hawkins positing that turbulence might be described by a sequence of Hopf bifurcations, to people numerically demonstrating that there actually are Hopf bifurcations in fluid flows, to Baird Nowak and team actually writing down the model that explained this Hopf bifurcation in this flow past the cylinder as you increase the flow velocity or Reynolds number. And there's a really interesting kind of conundrum that came up in this thought process, which is, for those of you who know dynamical systems and the Hopf bifurcation, this is a cubic nonlinearity. It's a cubic nonlinearity that gives rise to this bifurcation. But the Navier-Stokes equations have a quadratic convective nonlinearity. So how do you have a cubic Hopf bifurcation in a system with a quadratic convective nonlinearity? And so to some extent, that's really the magic of what Nowak et al. Did, was they reconciled these views. And what he showed was that there is a slow manifold here. So x and y are my two first principal components, the dominant energetic coherent structures that define my flow. But you have this third direction, z, which is related to the kind of the length of the mean flow or the average flow, and that is a fast variable. Okay, so z is a fast variable. Lambda is fast compared to mu, and what that means is that z very rapidly equals x squared plus y squared. I start off this manifold, I very quickly go up, and then I slowly line up until here, where I get vortex shedding in those two principal components. And if I plug in x squared plus y squared in here for z, I recover the effective cubic Hopf nonlinearity. What we found, see, I'm not that good of a learner. What we found was that our model had quadratic nonlinearities. It had a slow, fast timescale separation, so we recovered this quadratic slow manifold here. It essentially explained all of the dynamics that it took 30 years of experts to cook up and bake in. Okay? So we were very encouraged that we could actually use this as a tool for discovery. Now, what am I forgetting to tell you here, or neglecting to tell you? I built completely on the knowledge of Nowak et al. We used their coordinates. He told us the three things to measure, and then everything was trivial. Okay, so we still had to know what to measure and what were the right coordinates. But fortunately, in fluid systems, orthogonal proper POD modes or PCA modes tend to be great, and you tend to get polynomial models out. Okay? And again, modeling is this balance between accuracy and efficiency, and I want to emphasize, I think this is a great model where we can emphasize that by promoting sparsity, by only allowing the fewest terms that are necessary to describe the dynamics, you end up getting models that are both interpretable, so I can literally talk about what every single one of these terms does, and we can have a conversation about that. You can see the slow manifold here. And it tends to also be generalizable. If I start with an initial condition that is off my attractor, and this is in the paper, it very rapidly goes on to the right manifold and then converges to the true solution. So these are generalizable models because we captured the essential physics by throwing out all of the distracting variables. So within about 2 weeks of this being on the archive, I got an email from Jean-Christophe Loiseau in Paris Tech. And he said that there were some key things wrong with this model. These growth rates mu were incorrect. I actually maybe should have mentioned that there was a constant term added here that was wrong. So there was a missing fixed point, at least in the first model. And so, I was a little upset, but in reality, like, we were still pretty happy. We could still get this interpretable model that told a lot of the physics. So a few weeks later, JC emailed back and he said he solved it. Okay. And the way he did it was by these kind of two key innovations, and this is where the physics comes into the machine learning. And so this is, I think, really exciting. In the Navier-Stokes equations, the incompressible Navier-Stokes equations, we actually know how energy is conserved. We know that energy is conserved, and we know how energy is conserved. This manifests itself in a skew symmetry in the quadratic nonlinearities. So energy can be mixed from mode to mode, but it doesn't go anywhere. It just gets mixed around. And that happens through skew symmetric quadratic nonlinearities. There is a structure in the quadratic terms of the Navier-Stokes equations. And it turns out that you can actually enforce that structure when we do this Cindy algorithm. We're doing a least squares regression, then we throw away the small terms, and then we do another least squares on the remaining terms, and we throw away the ones that are small now, and we do that over and over again. And so you can enforce linear constraint equations in that Cindy regression, and you can enforce the skew symmetry constraints on the quadratic terms, and get models that are energy conserving by construction. So if you bake in that little set of linear constraints into the regression, you immediately get models with the right stability, the right properties, no overshoot, and it all works. And maybe the last thing I'll point out, we were looking for a model with quadratic nonlinearities because that's what history told us was interesting. That's what Navier-Stokes said the dynamics had to be. But it turns out that if you allow yourself to have higher order terms, cubic, quintic, septic, I'm proud of myself, now ninth order is nonic, I learned that. You can approximate the effect of all of those low energy modes that you truncate. And in some sense, you get a rudimentary closure model for this laminar flow system. Now, that is a long way from a turbulent closure or something you can actually use in multi-scale physics. But in this case, if I allow myself to have a 7th order model in X, Y, and Z, I get an exquisite model for this that captures all of the energy and timescales in the dynamics. Okay? So baking in a little bit of knowledge and allowing yourself a few extra degrees of freedom really makes a big difference. I don't have time to tell you all of the other cool stuff about PDEs and discrepancy models. So I think here I'll just summarize. We have high-level goals of model discovery, finding good coordinates. The modeling goals, of course, balance accuracy, efficiency, generalizability, interpretability. And with that, I'll stop and I'll take any questions. Thank you.
Floor is open for questions. Yes.
Can you use these methods to discover non-linearities that don't necessarily lend themselves to polynomial form?
Yeah, so that's absolutely possible. When you design that library theta, you can choose any basis you like. It can be overcomplete, you can choose anything. You can choose polynomials, trigonometric functions, Bessel's functions. And so to some extent, you have a huge amount of freedom. And that's actually one of the areas where, that's one of the areas where we're actively looking at now, is how to design those libraries to be more expressive for new types of physics. So we know in certain physics what the library should look like. In a new physics, how would we kind of learn the types of nonlinearities that we expect to see?
More questions? So.
As you increase the degree of the polynomial that can potentially explain some of these dynamics, do you tend to see that, so say you add an 11th power or 15th power or 7th power, does that power tend to always come into the basis disproportionately, or are you likely just as likely to eliminate it and focus on the lower term?
So again, that's something you do at that sparsity parameter. So you actually can get a hierarchy of models from simpler and slightly less descriptive up to more complex but more descriptive.
But do the higher powers persist disproportionately in that hierarchy in your theory?
If you get the wrong basis, high powers kind of have large amplitude. So that's the signature of when it doesn't work, is when you get a lot of power in high power, high order.